Welcome to the double angle formula. These formulas are ones that you actually need to remember. They do not appear on your reference sheet, but using the last video that we watched in regards to compound angles, we can actually use and get these formulas. So we'll have a look at how these come about anyway. But these are double angle formulas for sine 2 alpha, cos 2 alpha, and tan 2 alpha. So proving the double angles, let's start with sine 2 alpha. So if we start with our rule that we had, sine alpha plus beta, and we replace beta with alpha, you get sine alpha equals 2 sine alpha cos alpha. So we can use what is on the reference sheet, the sine alpha plus beta formula, to come up with sine 2 alpha if you don't remember it. Cos 2 alpha using the same idea. So cos alpha plus beta is cos alpha cos beta minus sine alpha sine beta. That's on the formula sheet. Replacing beta with alpha gets you cos squared alpha minus sine squared alpha. Now, this can obviously be manipulated as well. So cos 2 alpha is cos squared minus sine squared. But using one of our trig identity rules, sine squared plus cos squared equals 1, we get our other two formulas. So cos 2 alpha can be 2 cos squared alpha minus 1, or it can be 1 minus sine squared alpha. These will become very important when we actually get into integration and integrating with squareds. And finally, the tan 2 alpha. So we start with our tan alpha plus beta. We replace beta with alpha, and we get tan 2 alpha is 2 tan alpha over 1 minus tan squared alpha. So here's a couple of ones to try. So we're going to prove that sine theta plus cos theta all squared is 1 plus sine 2 theta. We're going to simplify cos 22.5 degrees and find tan of 2 sine minus 1 of 2/3. So for the first one, if we expand that, so square the first, twice the product, square the last, get you sine squared plus 2 sine theta plus cos squared. Hopefully you recognize that sine squared plus cos squared is 1 plus 2 sine theta cos theta. And since sine 2 alpha is equal to 2 sine alpha cos alpha, then 1 plus 2 sine theta cos theta becomes 1 plus sine 2 theta, hence proven. Next one, cos 22.5. Well, cos 22.5 is actually comes from the double angle where we use 45, but 45 is double 22.5. So cos 45 is equal to 2 lots of cos squared 22.5 minus 1. So we're going to manipulate that to get the cos 22.5 by itself. So we're going to rearrange the equation. So add the 1, divide, change cos 45 into 1 over surd 2. Get it as a common denominator. That's the final step on this page, or this one. Get it as a divide by the 2 and rationalize the denominator, and then finally take the square roots. Now the square root is the plus and minus, but because cos 22.5 is in the first quadrant, the answer is a positive. So that's positive surd 2 on surd 2 plus 2 over 4. I mean, we could just leave the square root over the whole top and just have 2 on the bottom, but that's an exact form as it is. And finally, tan of 2 sine minus 1 of 2/3. So in a previous video, we looked at inverse trig functions, and we allow y to equal to sine minus 1 of 2/3. So if we move the sign across, sine y is equal to 2/3. So putting it into our triangle and using Pythagoras to find the other side. The other side turns out to be the square root of 5. So now tan of 2 sine minus 1, well, since sine minus 1 of 2/3 was y, that's tan of 2y, and that's one of our formulas. So we get 2 tan y over 1 minus tan squared y, where tan y is equal to 2 over the square root of 5. Putting that in, we get tan 2y is equal to 4 over surd 5 over a fifth. We should know that that's when you do 4 over the surd 5 divided by a fifth, the 1/5 flips and you get 20 over surd 5. So you get 20 over surd 5, and rationalising the denominator, tan of 2y is equal to 4 surd 5. Thank you.